Ever imagined what would happen if Einstein, the genius who theorized the existence of black holes, was proven wrong? Let's dive into this mind-bending concept. Black holes, as we've come to understand them, are regions of space where gravity is so strong that nothing, not even light, can escape. At their core lies the singularity, a point where all the black hole's mass and gravity is centered. This is the concept that Einstein gave us. But now, picture this. A bold claim from New Zealand's Dr. Royker, a mathematician who first described black holes mathematically in 1963, suggests that this singularity, this very core of a black hole, does not exist. Can you grasp what this implies? If the singularity, the actual black hole, doesn't exist, does that mean black holes are a lie? To unravel this mystery, we need to dive into the birthplace of these concepts, Einstein's general theory of relativity. Let's start by visualizing it. Imagine a bucket filled with water. This is our universe. Now drop a ball into it. The ball displaces the water, causing it to curve around the ball. This ball is like a planet or star, and the water represents space-time. The way the water curves around the ball is akin to how space-time curves around a massive object. Now this is where Einstein's genius comes into play. He proposed that gravity isn't a mysterious force pulling objects together. Rather, it's a natural result of this space-time curvature. Objects, from apples to planets, move along the curves created by more massive objects. Think about it this way. If you've ever seen a marble roll around the edge of a funnel, you've seen this principle in action. The marble, let's call it a planet, isn't being pulled towards the center of the funnel. Instead, it's following the curve of the funnel. In the same way, a planet isn't pulled towards the sun. It's simply following the curve in space-time that the sun creates. However, it's crucial to understand that we aren't using gravity to explain gravity here. It might seem that way, but in reality, the curvature comes first, and the gravity is a result of that curvature. It's not the other way around. Furthermore, Einstein's theory also tells us that everything, including you and me, is in a state of free fall, moving along these curves. When a massive object like a star or a black hole curves space-time, we shift from moving in a straight line to a curved one. And because of this curve, our path leads us towards the center of the massive object, creating what we perceive as gravity. In essence, gravity, as we perceive it, is merely a result of this space-time curvature. This fundamental concept is the root of our understanding of black holes and the universe itself. Now, let's delve into Dr. Royker's groundbreaking theory that challenges our understanding of black holes. Picture this. A brilliant mind from New Zealand, Dr. Royker, who first mathematically described black holes back in 1963, has proposed a revolutionary theory. He contends that the singularity of a black hole, that is, the point where its entire mass and gravity are concentrated, does not exist. This concept is a direct contradiction to Einstein's belief, shaking the very foundation of our understanding of these celestial anomalies. So what does this mean? Well, if the singularity of a black hole, which is essentially the black hole itself, does not exist, does this call into question the very existence of black holes? And if so, how do we explain the image of a black hole published by NASA in 2019? Dr. Royker prompts us to consider an audacious possibility. Can black holes exist with their event horizon, their boundary in space-time from which nothing can escape, even without a singularity? Could there be an alternate source of their intense gravity? If so, what could possibly be hidden deep within these mysterious entities? To unravel this enigma, we need to return to the root of it all, Einstein's general theory of relativity, from where concepts of black holes, singularities, wormholes, and dark matter all sprouted. It's a complex web of theories and possibilities, and understanding it is crucial to grasping Dr. Royker's radical proposition. Bear in mind that the general theory of relativity suggests that every object is in a state of free fall, moving in a straight line. But when a massive object like a black hole curves space-time, we transition from straight free fall into curved free fall. The curviness of the path redirects our fall towards the center of mass, creating an effect much like gravity. So what truly lies inside a black hole?